We're now going to continue chapter 6. This is part 2. Remember, if you haven't done this already, pause the video, go print out or pull up the cheat sheet for quantum numbers that I put up there for you. It's in the helpful information chapter 6 worksheets. So what we're going to talk about are the quantum numbers, the principal, angular, magnetic, and electron spin. We are also going to talk about the rest of this chapter, electron configuration, and really the ins and outs of where each electron is in each atom. So first we have the principal quantum number. This number is the letter N, and it designates for us the size of the orbital. Okay, remember from the last lecture, the energy levels, we said N was equal to 1 or to 2 or to 3, and etc. And they started, number 1 starts closest to the nucleus with the lowest energy level, going all the way up to infinity, further away from the nucleus, and the farther away from the nucleus you get, the higher energy levels you get. Now, the size of it is the energy, and you can kind of imagine that when we have this atom with the dense nucleus and then the fixed energy levels around it, they just keep getting larger and larger and larger, etc. So angular momentum quantum number, L, it tells us the shape of the atomic orbital. So in the shape of the atomic orbital, S is spherical, P is a figure 8, D is a 4-leaf clover, which I am terrible at drawing. There, like 2 figure 8s. And F, I'm not even going to attempt to draw. It's very large and very complicated. Now, if you can remember or imagine how we talked about planes, 3-dimensionally, there are X, Y, and Z planes. So here's Z, here's X, and here's Y. If we were to have a p orbital, it could be on any one of these axes. We could have one on the x-axis. Okay. We could have one on the y-axis. We could have one on the z-axis. Okay. So p orbital will take a figure 8 shape. Those electrons in the p orbital will take on a figure 8 pathway, okay, on either the x, y, and z axes. The angular momentum quantum number, L, with some really important parts about it, it's a collection of orbitals with the same value of N. That's why we had those 3 figure 8s. Okay, the same would occur for D, but it would have 5 cloverleaf shells. And the one or more orbitals will have the same N and L values. When they're the same, that's referred to as a subshell, and we'll talk about that when we talk about electron configuration. So if you have a shell that's designated by N equals 2, that means it's in the second main energy level, so the second out from the nucleus, and it has 2 subshells, L is equal to O and L is equal to 1. And it's the allowed values of L that for L where N is equal to 2. Okay, these subshells are called 2s and 2p subshells, where 2 denotes the value of N, S, and P denotes the value of L. And so when we get into electron configuration, I'm going to do a lot of drawing and explain this kind of over and over and over. Then we have the magnetic quantum number, M sub L. Okay, it's the magnetic quantum number. This tells us the orientation. Where in space is this? And generally, we can say that there are 2L plus 1 values of ML. 1 or 2, okay? When N is 3, L can be 0, 1, or 2. In this particular example, they're saying N is 3, and they're telling you in this case, L is 1, okay? When L is 1, what were the values possible for ML? The only options possible were -1, 0, and +1. Now, the electron spin quantum number, M sub S, this has to do with which way the electrons are spinning. Each orbital can occupy 2 electrons, okay? And those electrons cannot spin in the same direction. It's like trying to get 2 of the same ends of a magnet to connect, and they won't, okay? So we represent this numerically by saying either +1/2 or -1/2. The plus and the minus in chemistry often has to do with directionality. In drawing electrons, we're going to use half arrows. So we'll use a half arrow to indicate one of the pair and another half arrow to indicate the other half of the pair. But note my half arrows are opposite to show that they are spinning opposite of each other. So with this electron spin quantum number, we have paired electrons, that's the takeaway, and they can either be +1/2 or -1/2. Plus and minus indicate directionality of the spin, and if one is positive and one is negative, that means they are spinning opposite of each other. So here's just a brief summary of what we have. Make sure you are understanding this pretty well. Use your quantum numbers cheat sheet to help you. There's several different ways of looking at quantum numbers and comparing what each thing can be given a different scenario. And I picked a couple that I thought were the best to describe it and to help you better visually see what's going on given different scenarios. So now we're going to talk about these S, P, D, and F orbitals. We are not going to go higher than F, and we're doing very little with F. I'm pretty much going to stick to the first three, 1, 2, 3, 4, 3 or 4 periods on the periodic table. So the S orbital is a sublevel of any main energy level, okay? And the S orbital, as a sublevel, can hold up to 2 electrons, and it is a spherical shape, okay? P orbitals are the figure 8 ones we were talking about, and P orbitals can hold a total of 6 electrons, and so that means there will be 3 sets of pairs if it is a full sublevel, okay? And here's your X, Y, and Z axes. Just a different representation of what I drew earlier, not much nicer than mine. But on this orbital, think of orbitals like a pathway. Like, you know, when you walk on a trail, you have a path that you're supposed to be taking. That's kind of the pathway all of these electrons we're talking about are going to take. It's not that they're in here anywhere. It's that they're going along this walkway, okay? Again, d orbitals, they are the cloverleaf shape. Okay, and then there's 5, they can hold up to 10 total electrons. And so there'll be 5 pairs. And all of them, all 4 are cloverleaf, and then the 5th one is what we call a donut. So it's got kind of like a figure 8, but then a ring around the middle. We call that the donut. Oh, look, here it is. So this is our donut, and that's the pathway the electron takes. All the rest are X, Y, Z, and X squared minus Y squared, different axes, okay? So you can kind of think of it where P was X, Y, and Z, right? Like, so now with our axes for D, we're gonna have, we can say, we'll call this X, Y, Z. Now we'll say XZ, right? And then if you could think of one kind of coming out at you, if you can think of an axis coming out at you and then going into the board, you know, into the board three-dimensionally, it would look like that as well, okay? That's the 5th one. F orbitals, I'm not even going to bother drawing. They're in the inner transitional section. It's those elements that are the inner transitional elements that have the F orbitals. And we're not going to worry too much about the shape of it. And, you know, the L values, we know they're greater than 2. Anything that is got an atomic number greater than 57 will account for F orbital behavior. So in this example, go through these and use your charts to try to figure everything out given the exact parameters that they tell you. So in this case, list the values of N, L, and ML for each of the orbitals in a 4D subshell. Okay, so use your chart to do that given the different parameters. Okay, before we can finally get into electron configuration, there's a few things we have to talk about first. Now this chart is an energy chart that shows us in each sublevel kind of how you can see how the energy increases. And in the first sublevel, this would be N equals 1. This would be N equals 4. You can see that there's only an S sublevel. In the second main energy level, there are S and P sublevels. In the third main energy level, there's S, P, and D. Guess what? In the fourth, it's S, P, D, and F. And these all look pretty linear on the same line. In fact, they are. They're drawn all on the same line, which kind of makes you think the 4P, 4D, and 4F maybe have the same amount of energy. The reality is they do not. They're actually more like this, where an S sublevel has a lower energy than a P sublevel, and a P sublevel has less energy than a D sublevel. And actually, this chart is even not 100% accurate. Well, meaning when you look at it, you might say, well, gosh, here's 3P. Now there's a 4S, but 3D's over here. What's going on? Well, it is accurate. It's exactly the way it should be, even though it looks like it's out of order. And the reason for this is the D sublevel actually has a higher energy than S. And electrons are going to fill in order of lowest energy to highest energy around the nucleus. They're going to fill these orbitals in a very specific lowest to highest energy order. So that means if we were going up and filling from our nucleus here, here's our nucleus. As we're going up and filling out away from the nucleus, all the electrons are going to try to stay as low as energy as possible. So if that means 4S is a lower energy than 3D, it's not going to stay in 3D just because the number 3 comes before 4. It's going to go to the shell that has the lower energy, which in this case is 4S. So a few more principles that we have to understand. There are 4 of them. The first one is Pauli's. Pauli's exclusion principle says that no 2 electrons in the same atom can have the same 4 quantum numbers. Okay, they have to be different. And that really has to do with this very last ms being -1/2 or +1/2, and it's the opposite spins. Pauli's exclusion principle says if every single number of two electrons in the same atom had every single number exactly the same, that means the electrons would not be having opposite spin. So if we look here and we say, okay, well, what's happening? What is this spin in these numbers and all this stuff? What does it really look like? Well, when we're going to start writing electron configuration, it's going to look something like this. You're going to have a coefficient, a letter, and a superscript. So the coefficient tells us which main energy level we're talking about, or N equals whatever number it is, in this case 1. S, or whatever the letter is going to tell us which pathway it's taking. Is it S, P, D, or F sublevel? And the superscript is going to tell us how many electrons occupy that space. Okay? So if you look at the periodic table, you can see that hydrogen only has 1 electron. So the only place an electron can be, if this is, again, my nucleus, here's main energy level 1, main energy level number 2, main energy level number 3. So we have 1, 2, 3. 1 only has S. 2 has S and P. 3 has S, P, and D, etc. Okay, so if hydrogen only has 1 electron, the only place it could be is in the 1s sublevel. So here's main energy level 1, here's S. The only place it could be is right there because it's going to fill closest to the nucleus first. Helium has 2 electrons, so both of its electrons will go into 1s, and there are 2 of them. So main energy level, S sublevel, 2 electrons filling it. The Aufbau principle basically says that you can build the periodic table, if you will, to determine their electron configurations. All right, and this is kind of a trick. This one is the trick to use the periodic table spot by spot to determine the electron configuration. And we will do that at the very end after we've really gotten into how to do electron configuration. So I'm going to ignore this for right now. We'll get back to it. Hund's rule says that the most stable arrangement of electrons is equal to the energy where the number of electrons with the same spin is maximized. So for example, let's say I was talking about carbon. If you look at the number of electrons carbon has, you will see that it has 6 electrons. So if I'm looking at carbon, there's my nucleus, okay? Here's carbon. Carbon has 6 electrons, okay? Now, if I were to say, here's my nucleus, here's my first main energy level, which only has an S sublevel. Second, we said has S and P. Now, carbon only has 6 electrons. So it's going to start filling from the closest to the nucleus first and then go up or away from the nucleus. So the first 2 electrons are going to fill this main energy level, the first 1s main energy level, which means I am going to have 4 electrons left. Once I have those 4 electrons left, I have to figure out where they're going to go. The next lowest is 2s. So the 2s is going to be filled with 2 oppositely spinning electrons. That leaves me with 2 electrons left. Now, the way we do this, according to Hund's rule, is that we're going to fill each empty spot first, then go back and double up. So what I would do is I would say, okay, 1 in this orbital, perhaps maybe this is the x-axis. This would be y, this would be z. And then fill the last one in the y-axis, figure 8 orbital. Okay? What we would not do is this. We would not say this. That is not as stable as spreading it out. It's better to have singles filling each sublevel that it can and having half filled shells than it is to have 1 doubled up and 2 empty. So here, for example, if I were to be drawing out oxygen, oxygen has 8 total electrons. So I would say fills 1s2, okay, so it's 8 total. So 2 are going to go into here, and that's going to leave me with 6. Then 2 more are going to go into here. That's going to leave me with 4. Now what these rest of the electrons are going to do is they are going to go fill 1, 2, 3, then go back and double up. Okay? That's just the rule. Memorize it and move on. Okay, so ignore these because I'm going to give you your own problems here. Let me get the periodic table here. Okay, so when we write electron configuration, again, we are writing 1s2, 2s2, 2p6, 3s2, etc., etc., etc. What this shows us here is that for potassium, for example, potassium has a total of 19 electrons. Keep in mind, I just want to notate something that I haven't quite said very clearly yet. All of this electron configuration, for so far, we are assuming neutral elements. They have not lost or gained any electrons. So it's whatever the atomic number is on the periodic table. When we get into gaining and losing of electrons, our electron configuration will change, and we'll talk about that. So here, if I am talking about these numbers, what this tells me is that potassium has 2 electrons in 1s. It has 8 electrons in 2s, 2p. Okay. It has 8 electrons in 3s, 3p. And then finally, it has 1 electron in 4s. Okay, that's the big, long, drawn-out way of writing out the electron configuration. This is how we notate it. Now, if you were to look at argon, and if you were to draw out the electron configuration for argon, you would find that it's this right here. That is the electron configuration for argon. So our core notation allows us to shorthand the electron configuration. So we can, instead of writing all of this, we could just simply put in brackets argon and then whatever is different from argon and what's left over. I think of it as like a remainder. So if you look at potassium on your periodic table, potassium is in period 4. And so the closest noble gas before it is argon. Argon is the very last noble gas in period 3. So it's always the noble gas before the element you're looking at. If I wanted the electron configuration for calcium, we could say is argon 4s2. Calcium has 1 more electron than potassium. It's just to the right of potassium on the periodic table. We're looking at platinum. By the way, I love platinum. Platinum was one of my favorite ones to give on a test. Just putting it out there. All right. Platinum, if you were to go from its noble gas, xenon, okay, then we could count 6s2. Now we got to deal with and just know that in the 4 are the F series that come before D. So it would be 4F14. Now we're in the D's. So it's 5D, 1, 2, 3, 4, 5, 6, 7, 8. And then we have to include the 1 from the 9. So it would be 5D9. Okay? All right. There are 2 anomalies with electron configuration. Normally, we would think that chromium in its last digits would be 3D 4s2. Okay, that would normally be the rules we follow. The problem is, it is much more stable for chromium to have a full half D sublevel. Okay, so it's better for it to have 1 electron in each section of the D sublevels than it is to have 2 electrons in the full 4s. Okay. The other anomaly is copper, and for the same reason. It's better to have a full D sublevel than to have 1 electron missing and a full S sublevel. So here, if we're looking at this, this is what it looks like. It's more stable to have this makeup and this makeup, either a full or half d orbital and only one electron in the s, than it is to get rid of this and have this, or get rid of one of these and have these. Okay, that's not as stable. There are many other anomalies. It's basically when we see it, if we can fill fully with what would be s electrons, but fill fully or half fully a d sublevel, that will always take precedence over a full s sublevel. So here's an example. Write the electron configuration for an arsenic atom, Z equals 33, in the ground state, meaning it has not gained or lost electrons. Okay. The setup is that the noble gas core for arsenic is Ar, argon, where Z equals 18 for Ar. So the order of filling is writing the Ar in brackets and then just continuing whatever left. Here's calcium. Its closest noble gas is argon. So we can just simply say argon. And then 4s1, 4s2, so it's 4s2. If we were to do it the long way, we could simply say, we could say 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3, 4, 5, 6. And then 4s1, 2, stopping on calcium because that's what I'm doing it for. So I'm pretending like each box represents an electron, and reading left to right, top to bottom, I can count the spaces knowing the S, P, D, and F sections of the periodic table. Again, this is just a little trick to help you and to make it go a little bit quicker. Okay. Again, for calcium, argon is the closest noble gas, and you will see that this is the electron configuration for argon. So the short way of writing it is argon 4s2. The long way is writing it all completely out.